Okay, welcome to the next class on variational methods for computer vision. Today we will get to one of the core components of the entire class, and that is the variational calculus. So in the last sections we've seen, in the last chapters, we've talked a little bit about filtering, image filtering, and in particular diffusion filtering. And you may be wondering how that relates to variational methods, and I think this will become clearer in this section. It somehow all builds up to a more principled approach to do image restoration and image analysis. So a few words to start out on variational methods. Variational methods are a specific class of optimization methods. So optimization is something that is widely known to a lot of people. The key idea is that you define some cost function or quality criterion, and then you optimize that, and you find solutions to a particular problem by minimizing a certain cost or maximizing a certain gain. Typically, minimizing or maximizing is in some sense equivalent. For the variational methods in particular, the key idea is that the solution space is a continuous space, and that you have some kind of extremality principle that defines your optimality. And this is something that many of you will be familiar with from high school still. The idea is that if you have your solution space, let's call it U, the conceivable solutions, then you have some cost function E of U, and then, as you may recall, the minimizer of the cost function is a location U optimal, where the derivative of E with respect to U must be 0. And as you know, this is a necessary, typically not sufficient condition for minimality, but it's a necessary condition. And the variational calculus aims at computing solutions by finding solutions to that extremality principle. And this is the idea of varying the solution, because the idea is that if I vary the solution around the optimum, then the cost function locally does not change. This is the idea, the derivative must be 0, and so this is the key kind of aspect of variational methods. It turns out that you can solve a number of computer vision and other types of problems with variational methods, and the advantage, at least compared to what has been done in the past, is that you don't have a heuristic sequence of processing steps, but you actually define beforehand what you want, what properties your solution should have, and you put these properties in the variational principle, and then you can automatically derive an algorithm. This will make more sense, this statement, to people who know a little bit more the history of image processing. And if you go into the 1970s or 80s and look at what people did in that period for image processing, many papers start with, let's take an image, let's take all the pixels, and now we take the brightness value at some central pixel, we take the neighboring values, we average them in the following fashion, then we do some thresholding, then we compute some derivative, then we do this and that. It reads like a cookbook, you know, one step, next step, next step, but you don't have a clear understanding what is the author really aiming for, what are the assumptions that he makes to get the solutions. It's really just a cookbook recipe. And this is where the variational principle comes in, the variational or optimization approaches, which are in some sense a more principled and more transparent way to solve problems. You don't start with an algorithm, but you start by defining what is it that my solution, what properties should my solution have. Turns out the variational calculus, it was then in the image analysis field pioneered in the 80s and 90s, and it is now one of the leading and top performing approaches to do a lot of things in image analysis, image denoising, deblurring, super resolution. We'll see a couple of examples along throughout the class. Segmentation is something we'll talk about a lot in this class. Motion estimation, dense 3D reconstruction, tracking. So many problems in vision can be solved by variational methods, but not only that, it turns out the variational calculus is one of the top performing approaches to get the best results to these kinds of problems. So before I get into a specific example, maybe a little more about the advantages of variational methods, and in fact, as you can see, advantages of optimization methods in general. So these advantages not only apply to the variational methods, but also other optimization techniques. So one nice feature is once you've defined a cost function, you can analyze the problem from a more formal level. You can basically check for these criteria, does there exist a solution? Yes or no? Without actually computing something, you can just study the cost function and determine, does it admit solutions? If yes, are the solutions unique, or are there possibly multiple solutions, maybe even infinitely many solutions? And are the solutions that I can compute in this way, are they stable? So stability is an important aspect. It basically means if I change the initial conditions just a tiny little bit, is the solution gonna be preserved? Is it gonna change a little bit? Or is it gonna change drastically if I just change like the brightness of one single pixel, for example? And in practice, it turns out we tend to want stability, because we want solutions that are robust in some sense to perturbations of the initial conditions. If you have an algorithm that generates a completely different solution just if you change tiny little bits in the brightness, that is typically not a good thing. And so all of these things can be studied on this more formal level. For example, in a traditional multi-step processing approach, you cannot do that. It's just not accessible. They're often complex, they're intransparent. And another thing about these multi-step processes, we'll see examples throughout the class of methods from the 70s or 80s, and then you'll get a better idea of what the issues are. But one of the issues is if you have such a multi-step approach, if you change one of the modules or components in the algorithm, you typically have no understanding what happens to the subsequent modules, right? If I say, oh, in step 5 of the algorithm that has 10 steps, someone does a threshold with some parameter theta, what if I change the parameter theta? Then step 5 will give a different solution, and that will affect all the subsequent processing modules in a somewhat unpredictable manner. And so the consequence is that these traditional multi-step approaches, although some of them worked very well, they were very hard to adapt to new scenarios. Because if you go in and tweak, the whole system breaks down. Because the subsequent steps kind of assume a certain output of step 5, and if step 5 gives a different output, it's very much like in a factory where one worker builds up on what the previous worker did, and if you put a new worker in place 5, the whole thing goes bonkers. It's very common, and this is typical for these multi-step approaches. A nice feature about optimization methods is that they're very transparent. As I said, there are no hidden assumptions. Because typically in a multi-step approach, each processing step makes some kind of assumptions. Why is it computing a smoothing in step 6? Why is it computing a thresholding? There are certain assumptions, but often these assumptions are not made explicit. Whereas in the optimization techniques, you make very explicit what is it that you want, what is it that the solution should have. In addition, there are typically fewer parameters. There are parameters in optimization methods, but they're quite transparent. Not like the threshold value in step 6 of the algorithm, but all the parameters enter the cost function, and then they have a very clear meaning. And you have a good understanding of what happens if you change that parameter to the final solution. In addition, you can easily combine them and replace them. Essentially, rather than replacing one of 7 or 10 steps in a processing pipeline, what you do is you replace one of the terms in the cost function and then minimize the new cost function. And so you can easily combine optimization techniques essentially just by adding different cost functions that aim at different criteria. We'll see an example right now, and this example is one of the simplest examples in image analysis, is the problem of image denoising. Denoising means we want to approximate some input image, so let's call that image f. And approximate means that the function u that we compute, it should be similar to f. That's the first criterion that we want. Secondly, what is it that we want? Denoising, typically we want to remove small-scale oscillations, and so we assume that the function u that we want to compute should be spatially smooth, meaning from one point to the neighboring point it should not change too much. These are the two assumptions. We put them very clearly on the table. That is what we expect from the solution. And then we can combine these criteria in a cost function, which essentially has, in this case, two terms, a data term and a smoothness term. The data term measures how similar is any given function u to f, and the smoothness term says how smooth is whatever given function. And the idea is you can define such a cost function that can measure how good does a given function u fulfill my criteria. So rather than computing some ad hoc function, I first define on the space of all possible functions what's a good function. And I define a quality criterion that tells me what is a good function. A good function in our context will be one that has low cost, low data fitting cost, low smoothness cost. Now, we haven't said how we measure data similarity, how we measure smoothness. That's really up to you in some sense. We'll show some examples in the class. This looks like a very particular setting, but it turns out that most variational methods actually have this form. Most variational methods consist of typically two terms, a data association or data fidelity term that takes into account your measurements, and a smoothness or regularity term that tells you, we'll see a little later, it tells you how likely a priori is a given solution. If it's very oscillatory, it's not very likely to be the real image, and if it's smoother, it's more likely to be the real image. That's the assumption we put in here. And so this is what I mean by saying in the optimization methods, you put your assumptions on the table. Here they are. And there's typically some parameter, the regularization parameter, lambda it's often called actually. Interestingly, the name of the parameters is often the same in many papers. Of course, you could name that parameter alpha, beta, gamma, nu, whatever you want. But typically the weight of the smoothness term is called lambda. It just makes reading papers easier. If everyone changes the notation from one paper to the next, it takes readers a little more time to figure out what was gamma again, I don't remember. Whereas if you read a lot of papers on denoising with variational techniques and you see a lambda, you have a guess of what that is. So it turns out quite helpful that people name the parameters the same way. Now, I didn't say how we measure data similarity and smoothness. Here are two examples. For now, we will consider a discrete world to start with. So, and in fact, one dimension, so just basically a list of consecutive brightness values, right? And we'll call them f1 to fn, so there are n pixels, one next to the other, and we want to compute an approximation of that one-dimensional discrete image called U, and that has values, brightness values U1 through UN. Now I said we want U to be similar to F. There are infinitely many ways to define similarity, to measure similarity. The most popular one is this one. It basically says minimize the sum of squared differences. Find a function U that is similar to F at every pixel I. And similar in the least squares sense, if you want. There is a factor 1/2 here. This is just by convention. It doesn't really matter. Constant 4 factors are not important, really. But we'll see in a second why there is a 1/2. This is just a convention. So that measures data similarity, and what I should say is this is one possible choice. There are other choices. For example, you can just take the absolute norm and drop the square. And it turns out in some examples, in some scenarios, that may give better performance. So the key is that we want to impose similarity to the data. The next is a modeling choice, is how we measure that similarity. How we quantify if U is not exactly, ideally, the cost function is 0 if U is equal to F, because then similarity is perfectly fulfilled. But as soon as U deviates from F is slightly different, we have a freedom of how we measure that discrepancy. And so this is one choice. Similarly, we want smoothness. Smoothness, as I said, means from one pixel to the next, the brightness should not change. So we measure the change. For all pixels I through n, we say what is the brightness change from pixel I to the neighboring brightness. At the neighboring pixel I plus 1, and again we minimize the sum of squared differences from each pixel to its neighbor. The sum of squared differences again is a random choice. We could have taken another way to measure smoothness. We could here as well take the norm. We could take the square root of the norm for every pixel. There's many ways to measure similarity. This is the most popular choice. Why these two choices are the most popular ones, anyone want to take a guess? What is good about these choices? Why is a quadratic error useful? What do you think?
Convex function.
It's convex, very good, yes. So this is a parabola, so it's convex, that's a good thing. And if you compute the derivative of a quadratic cost function, you get a linear equation system. We'll see that emerge in a second. And linear equations are very easy to solve. So it just makes life very easy. So if you want an easy job as the person who has to minimize the cost function, take a quadratic cost. But if you want to get a very good performance in terms of denoising, quadratic penalizers may not be the best choice. So there is some trade-offs here. We'll see a little more throughout the class. So if we put the data term, here we have it, and the smoothness term together with a weighting factor lambda, so we have 1/2 this term and lambda over 2 times that term. This is the cost function we want to minimize. Maybe one more comment, lambda is usually the weight of the regularity term. Of course you could put the weight here as well. It doesn't matter. You want a relative weighting of the 2 terms. Where you put the weight is not important as long as you can balance them. So sometimes people put the weights here, or they put 1 over lambda here. If you divide the whole thing by lambda, then you have 1/2 here and 1 over 2 lambda there. And it turns out it's exactly the same problem. If I just scale the cost function by a constant factor, the optimality is not affected. The location of the minimizer is always the same. And this is important in optimization. The value of the cost function really doesn't have a meaning. It's completely arbitrary in some sense. What is relevant is the location of the minimizer. And so additive terms, constants that you add to the energy, have no effect on the minimization, and multiplicative factors also have no effect. Unless, of course, you multiply only one of the two terms. That, of course, changes the solutions. And in fact, if you increase that parameter lambda by which we weight the smoothness, what happens? You get smoother solutions. Surprise, surprise. So in that sense, this is what I'm saying. Optimization techniques have few parameters. Here we just have one single parameter, and the meaning of that parameter is completely clear. If you increase the cost of smoothness, then any solution that is not smooth is energetically disfavored. It costs more and more. And so the algorithm that minimizes the cost function will aim at fulfilling the smoothness, more importantly, if the weight is stronger. And so then, once we set up a cost function for denoising, as shown here, we can say the solution to our denoising problem is to the function u hat that minimizes the cost function, as shown here. And now this is where the variational framework kicks in. In optimization, the question is a very challenging question for any given cost function, how to efficiently find the function u that minimizes this cost. In the variational methods, typically you rely on the variational principle. I drew it on the board here. The idea that the derivative of that cost function with respect to u must be 0. And now, since our function u is a discrete set of n brightness values, u1 through un, there is actually n derivatives. There are n degrees of freedom in our optimization problem, and dE by du must be 0 really means that the derivative in each of these dimensions must be 0. So the derivative of E with respect to u1 must be 0, with respect to u2, u3, etc. So there are actually n equations in this. And this is often a little misleading. When you see dE by du equals 0, typically it's not one equation but many equations. And in the discrete setting with n pixels, this is n equations. What do they look like? Well, we can actually compute them, right? Here's the cost function. Taking the derivative with respect to u1 is not difficult. You can all do that. Here, u1 appears in the first term of the sum, f1 minus u1 squared. If you take the derivative, you get f1 minus u1, and the factor 2 cancels out. And in fact, that is really the only reason why we put 1/2 here, is that in the derivative, the factor 2 cancels out. Then we have u1 in the second term here, in the term u1 minus u2 squared. And so here again, we can take the derivative, and what we get is lambda times u1 minus u2. And the whole thing must be 0. So this is the first equation, dE by du1 is 0. And similarly, you can take derivatives for the other pixels, dE by dui for the inner pixels, so 2 to n minus 1, and you get one additional term. Why is that? Well, the pixel u2, let's look at where does u2 appear. Here, it appears in the second term of the sum, f2 minus u2 squared. Here, it actually appears twice. Once in the term u1 minus u2 squared, for I equals 1, I have u2 here. And then for I equals 2, I have another u2 minus u3 squared, because it's coupled to both of its neighbors, right? So the intermediate pixels are coupled to the left and the right neighbor. The boundary pixels are only coupled to the inner neighbor. And this is why here we have one additional term in here. So we have 2 times the central pixel minus the left minus the right pixel. And all of this is weighted by lambda, the regularity weight. So this is the equation for the inner pixels. And then for the rightmost pixel, we have that equation quite very much like for the left pixel. So we have tons of linear equations, as many as we have pixels actually, and we can now summarize, as you know, a lot of linear equations in a linear equation system, in a matrix equation system. And that equation system looks like that. You can actually validate what you do here to get from here to here is you just order, you put all the terms that depend on you on the left-hand side of your equation, and the constants, the fi's on the right-hand side. So you have the fi's on the right-hand side, and on the left-hand side you can check the first equation, for example, is u1 plus lambda u1 minus u2, right, equals f1. And similarly for the second equation you get this, so you get a matrix here. I didn't write here is actually 0. This is a convention. If there's nothing shown, it basically means it's 0. And so what you get is a matrix that is what's called tridiagonal. You have a diagonal and you have the two off diagonals that are just minus lambda here. So this is a tridiagonal matrix, and now you can see the solution is the vector u of brightness values that solves this equation. So that's all. And this is in some sense one of the advantages of taking a quadratic cost function as here, is because when we do the derivative we get a linear equation system. And here's the linear equation system, and so all you need to do is solve that linear equation system, and that gives you the denoised solution. How do we solve such equation systems? It turns out for this particular tridiagonal, as you know, there is this Gaussian elimination. This is something everyone has heard of in high school. Unfortunately, in practice, is not terribly useful. It's a very slow and tedious algorithm, but it is an algorithm that solves the problem iteratively. Here, this Gaussian elimination works because you have tridiagonal, so you don't have to do too many insertions, etc. Right? If you plug the first equation in the second, you can eliminate this term, etc. And so you just need to do one or two sweeps in a tridiagonal system to solve the equation. And in fact, for tridiagonal matrices, the Gaussian elimination is called the Thomas algorithm. And it's quite fast. It's linear time. So that's usually a good thing. In addition, you can show that the inverse of this matrix exists. Unfortunately, the matrix M is sparse. That's a good thing. But M inverse is not sparse. Sparse, by the way, means that most coefficients are 0. Sparsity is always a good thing when you handle matrices. Why? Because if you do, for example, matrix vector multiplications, if you have a sparse matrix, you don't have to do too many multiplications. Most of the coefficients are 0, so they don't actually play a role. Sparsity is good. What's not so good is that the inverse is not sparse. So if I were to compute the inverse matrix and then apply it to f, right, the solution U is just M. If this is M, M inverse times f, right? But if my matrix M is not sparse, this matrix vector multiplication is already computationally intense. And so this is slightly bad that it's not sparse. The minimization is unique, so there is only, it's invertible, the minimization is unique. Why? Because the energy is strictly convex. The quadratic cost function is strictly convex, so at the minimizer there is only one solution. Just to recap a little bit the terminology, this is more a class on variational methods. There are classes on convex optimization, but convexity plays, of course, an important role for us. And so I decided to recap a little bit aspects of convex optimization. For those who don't remember, a set is called convex if for any pair of points the connecting line is also contained in the set. So this is a convex set. How do you know? Well, as soon as you take any points in that set and connect them by a line, that line is completely contained in the set. So that means that the set is convex. A function E is called convex if its epigraph is convex. What that means is, let's look at the function. We have a nice convex function here. The epigraph is this set here. It's a convex set. For any points in this set, the connecting line is in the set. And so you can use the notion of convexity for sets and directly extend it to functions, where functions are convex if this epigraph is convex. Strictly convex means that the epigraph is strictly convex. Convex, by the way, so this is also a convex domain, but it's not strictly convex, because if I take maybe strict convexity is better for functions here. Let's not go too much into sets. Strictly convex means that this set is strictly convex means that the connecting line is strictly inside the set and not on the boundary as it could be here, for example. And you can actually rewrite that. Let's look at that. If we consider this as U1 here, that point, and this point let's call it U2. Then the fact that the line is contained in the set, or that it's strictly above the curve, it basically means that for any convex combination of U1 and U2, let's call it U alpha. This is U alpha is 1 minus alpha times U1 plus alpha times U2. And you can see if I go from alpha from 0 to 1, I go from U1 to U2, right? If I put alpha equals 0 in here, then I have U1. For alpha equals 1, I have U2. And for all the intermediate alphas, I basically move from here to there. And then what does this inequality say? It says the energy at that intermediate point, that is E of U alpha, is smaller or equal to the convex combination of values, and that is this point here. So that is, here you have E of U2, here you have E of U1, and this point here is just the same linear or convex combination of the energies. And so this inequality, it looks a little bit weird at the first glance, but it really states exactly the fact that the curve is strictly below the connecting line. Because this is the point on the connecting line, and this is the point on the curve E. And so this is quite useful. Often people memorize this inequality, but then don't really have an intuition of where it comes from. It just says if you take a convex combination in the U space and take that energy, this one here, it's below the same convex combination of the energy values, E of U1, E of U2. So this is, to recap, convexity and strict convexity of cost functions. Of course, the cost function is convex if you have less or equal here, and strictly less, and less basically means strict convexity. The cost function, as I said, is convex. This is a proof of it. I must admit here, for simplicity, I assume that s squared is convex. So the function, the quadratic function, is a convex function, something that you should already know. And so it basically means that this inequality is fulfilled for any S1, S2, and alpha in the interval 0, 1. This is the convexity that we saw on the last slide. And using that inequality, we can then show that E lambda, the cost function that we have, where is it here, is convex. How do we do that? Well, we take E lambda at a convex combination of U and U tilde. That reads like that. So Fi minus the convex combination at pixel I squared plus lambda over 2, and then the sum of the convex combination at U the convex combination at pixel I minus convex combination at pixel I plus 1. And then we can rearrange terms, and we can see that indeed we can rearrange the terms in such a way that the outcome is smaller than 1 minus alpha e of u plus alpha e of u tilde. Essentially what we used here or showed here in these steps is nothing but the fact that convexity is preserved in summation. If you have two terms that are convex, then also their sum is convex. Here we know the square is convex, and so the sum of these is also convex. Similarly here, it's just a summation of convex terms, and so it preserves the convexity. This is one aspect why the class of convex functions is a nice one. For example, there are other interesting functions. You know, in optimization we want to somehow assure that we can compute provable optima. For example, using the variational principle. Well, there is cost functions that are not convex and still have a unique minimum. For example, let's take a cost function like this one, right? That has a unique minimum. It's not convex though, because if you take any 2 points here, the connecting line is actually below the curve, right? So it's not a convex cost function. Nevertheless, it has a unique minimum. This cost function and this class of cost functions is called quasi-convex. So in principle, if your cost function is quasi-convex, that's also good because it means you can compute global minima. Nevertheless, quasi-convex functions are not studied very intensely. The reason is that if you take a sum of two quasi-convex cost functions, the outcome is no longer quasi-convex in general. So quasi-convexity is not preserved in summation. Whereas convexity is a very strong property. It's a property that is actually preserved in summation. And that's useful because it's not very helpful if some term in your cost function is quasi-convex. If you have multiple such terms and then you combine them, as I said, then you lose optimality all of a sudden. You don't want that. You want to preserve optimality results, and so working with convex cost functions assures that. This was the example of denoising in 1D. Of course, images are not one-dimensional, and it becomes a little more interesting if we take more dimensions, so 2 or 3 or 4 dimensions. Doesn't really matter. Let's take a D-dimensional image, and so there's lots of pixels in each dimension. I have N1 in the first, N2 in the second, and say ND in the Dth dimension. Typically, if you have a square image, they're all the same. What you can do is you can apply the same denoising strategy to a general image, and one simple way in terms of notation of doing it is just to arrange all pixels in a linear order. What does that mean? It basically means I take my pixel grid and I just number all the pixels 1 through n1 and then n1 plus 1, etc., and I just put them in one long vector. And so the size of the vector is large, n, where n is the product of all of these individual dimensions. And then I can write the denoising exactly in the same way. Almost exactly, not quite. The data term is the same. For every pixel in my image, I want the brightness at that pixel to be similar to the observed brightness Fi. That's the data fidelity term summing over all the pixels. For the smoothness term, again, I sum over all pixels, and then I say the brightness of a pixel of the central pixel, let's call it Ui, should be the same as the brightness of its neighbor pixels. Since we rearranged the pixels in a linear order, we lose that neighborhood information, or it's not really there. So we have to basically say, well, J should be the neighbors of I. what they are, right? If you rearrange them and you have a pixel here, then it's the previous and the last pixel are the neighbors, but also the one above and maybe the one below if you have one below. So there's up to, in a 4 connected neighborhood, in a general 2D image, you would have 4 neighbors here. And where they are in your vector doesn't really matter. They're somewhere, you can localize them. And so this is the smoothness term here for 2D images. It says the pixel should have a similar color to its neighbor pixels, again in a least squares fashion. And again, you have quadratic terms, quadratic data term, quadratic smoothness term, summations, preserve convexity. So the cost function is indeed strictly convex, which means the variational approach will give us the global minimum. How does it work? Well, again, we take the derivative with respect to ui for all the pixels I. These are all variables. dE by du must be 0, so it must be 0 in each of the dimensions. With respect to each of the pixels, the derivative of e must be 0 at the minimizer. So if we find a function u that fulfills this equation, or this set of equations, one should say, then that is the global minimum of our denoising. This matrix, you can write that as a matrix equation system. I'm not going to do it. The matrix is very large. And in the general 2D case, it's still sparse as before. Why? Because the pixel ui appears in equations only with the 4 neighbors, right? So there are only 4 other, so meaning in each row of your matrix, there are going to be 4 non-zero elements. 5 actually. The central pixel, 1 element for the central pixel, which has the value 1 plus lambda, as you can see. As before, right, we had 1 plus lambda for the central pixel, and then we had minus lambda for the neighbors, and this is exactly the same, minus lambda for the neighbors uj, except there are 4 such neighbors. And so compared to the total number of pixels, this is very sparse. But it's not tri-diagonal anymore. Why? Because the upper and the lower neighbor are not next to the one. They are further away in the ordering because there's a lot of pixels in between before you get to the upper one. And so you have some off diagonals, but not dramatic. But essentially it means that the Gaussian elimination, this Thomas algorithm that we saw before, is not as practical in this setting anymore. Because we don't have tri-diagonal matrix, we have a larger, more complicated sparse matrix. And so one of the questions that arises if we have this linear equation system that defines our optimum, how do we solve it? And this is not a class on numerics and on solving linear equations, but I did want to recap a little bit some of the techniques that people use. This matrix is a nice matrix in the sense that it's sparse. Most entries are 0. As I said, the inverse is typically not sparse. It's typically dense. It's often difficult to compute, and the problem with this matrix is it's very large. What's the size of this matrix? Anyone know? If we have large n pixels, what's the size of m? Yes? N squared, exactly. And so if you have a couple of megapixels in your image, you have megapixel squared dimensions for your matrix. So it's actually too large to store it in memory and to compute its inverse directly. So in practice, you don't do what you learn in high school. You don't compute m inverse first and then multiply m inverse with f. You don't do that because you cannot even store m inverse in the memory. But there are so-called iterative solvers, which basically solve this equation system by very simple iterative processing, just matrix vector multiplications essentially. And the two best known ones are the Jacobi method and the Gauss-Seidel method. And so I wanted to briefly review what they are about so that you've at least heard what the Jacobi solver is and what the Gauss-Seidel method is and what some of the extensions are. They're actually not very difficult. Here's the Jacobi method. It turns out the Jacobi method works to invert the matrix or to compute the solution, not invert the matrix, but directly compute the solution to your a linear equation system, and it works if it converges. It's an iterative algorithm that provably converges to the optimum if your matrix M is strictly diagonally dominant. That means your matrix M is such that the diagonal elements are larger than the off-diagonal ones. Larger in the sense that if I take the diagonal element MII, that is the element on the diagonal of the ith row, ith column, then it's larger than the sum of the absolute values of the off-diagonals. If that is the case, and we'll see in our equation system this is indeed the case, then we can apply the Jacobi algorithm. Let's look at this equation system. We saw it already in the 1D case, but very similar in the ND case. The diagonal elements are always 1 plus lambda. Or if we have two neighbors, they're 1 plus 2 lambda, or in a 2D image there are 4 neighbors, so the diagonal element is 1 plus 4 lambda. And the off-diagonal elements are all lambda. And so the norm of 1 plus 2 lambda, they're all positive. Actually, lambda is positive, 1 is positive. So this is 1 plus 2 lambda, and the sum of off-diagonals is 2 lambda. And clearly 1 plus 2 lambda is larger than 2 lambda. So the diagonal really dominates. Why is that useful? Well, assume we didn't have any off-diagonals. If we just had a diagonal, the problem would be trivial. Inverting a matrix that diagonal is easy. You just invert the diagonal elements. You're done. Right? And so the idea underlying these iterative solvers is that this diagonal plays the dominant role, and if we can assure that the diagonal has the dominant effect, then we can basically, the error we make by ignoring the off diagonals is not too bad, and it decays with the iterations. Here's this iteration. What we do indeed is we separate the matrix M into its diagonal and the rest. A is the off-diagonals, D is the matrix that just has the diagonal elements. Whereas A, of course, then has 0 on the diagonal. And we can always split any matrix into this, but the key here is that D really has the core component of the matrix, and A is very small. And so what we can do is we can just try to invert D, because that's easy to do. And how do we do that? We rearrange the terms so that the D term is on the left-hand side and the off-diagonals are on the right-hand side. So we have du is f minus au. And then we iteratively we invert D, right? So we start with some initial function u0, put that into the right-hand side, and solve then for the left-hand side for u1. And that is just d to the minus 1 times f minus au. Ideally, this equation should be fulfilled. So ideally, we want some function u such that this is 0. And in practice, the idea is that with every iteration, we get closer to the optimum. And upon convergence, uk plus 1 is uk, and then we have a solution to the algorithm. So you obviously see that once this iteration converges and uk plus 1 equals uk, it means nothing but that we've solved the problem. Typically, and what you see is if you look at this update equation, it's very simple. You just take the image minus a times u. A is sparse, remember, so this is not a lot of multiplications. You don't have to store the whole matrix A. You just, in sparse matrix computations, you just memorize where are the non-zero elements. And these are the four neighbors essentially, so you multiply the four neighbors by this minus lambda, and that's it. We'll see actually how that works in this denoising. And then d to the minus 1, this d is not really a matrix. For each row you just take the inverse of that diagonal element, and so it's just 1 over lambda essentially, or 1 over this diagonal term, as we saw here, is 1 plus lambda, or 1 plus 2 lambda with two neighbors. Sorry, I'm jumping. Yes, so this is the iteration of the Jacobi method. And you just iterate over k and consecutively compute better and better solutions, approximations to your solution. In practice, so this is very easy, low computation, very low memory cost, because you don't have to store these matrices at all. You just have to store the few elements that are non-zero. And the next good thing is it's very easily parallelized. Why? Because this is U for all pixels. And this is U for all pixels at the previous time, and so you can basically in one sweep update all pixels. And if you have a GPU, you can, this is very fast. Moreover, what you do in practice is you don't let this converge perfectly, but at some point you terminate when you're sufficiently close to your solution. And the question is often in these algorithms, when do we terminate? And there are many numerical iterative algorithms, and the termination criterion is usually a nasty business. Nasty in the sense that if you read the paper, typically the author doesn't tell you what his termination criterion is. And so this is a little bit of a tricky thing. It takes some expertise, some experience. Sometimes it happens that the termination criterion has to be adapted to the specific problem. Here you have a termination criterion that is fairly meaningful. Basically, we want m times u should be f, right? So ideally we should stop if m times u is equal to f. And so basically what we check is how far is it from f. How far is m times u from f? And that we call the residuum. It is how much is left to explain f with your function u. And what we can do is a meaningful termination criterion would be to say what is the residuum relative to the initial residuum. So initially I had a certain distance between m times u and f, and then I say what is the residuum relative to its original one. If it's gone below epsilon, so I'm at epsilon times the original residuum, then I stop. And depending on how you set epsilon, the algorithm will be slower and more accurate, or faster and less accurate. So that looks like a solid termination criterion, but you already see it's a little bit of a heuristic here as well. Why is that? Well, if I initialize with a good solution, then the algorithm will run longer, because then R0 is going to be very small, right? And getting into epsilon of times R0 of the residuum of the initial is going to be more difficult. So if I initialize better, then then it will go closer to the correct solution than if I have a bad initialization. So all of a sudden your result depends on how good your initialization is. And so you see this is always, as I said, some issue with termination criteria. To find one that works like a black box is not easy. And in general not possible. So what does it look like for the image denoising in our case? Here are the equations, the linear equations. Here you see ui plus lambda times the number. This norm n basically means the number of neighbors. In the denoising for 1D images there were 2 neighbors, so we had 1 plus 2 lambda here. If you have 4 neighbors, you have 1 plus 4 lambda times ui. And this is the diagonal term, right? This is the terms that depend on ui, the central pixel, and these are the terms, the off-diagonal terms, and the constant. So fi is the constant, and lambda times the neighbor values is the off-diagonals. And then what we do is we basically plug here the old solution of u on the right hand side, and here the new solution at iteration k plus 1 on the left hand side, and we divide by 1 plus lambda times the number of neighbors, and so we get this iteration. And so this is what I mean by it's a very simple iteration. You have brightness values at all pixels at some initial configuration, and this is the update rule that gives you the new brightness values. And we initialize somehow appropriately. For denoising, there is a very good natural initialization, and that is start with the input image. Why? Because the data term says I want to be close to the input. So starting with the input is always, so this is a solution that fulfills the data term perfectly, and from there on I iterate. What do the iterations do? This looks a little complicated at first glance. What it does is essentially, you can see it this way, the brightness at pixel I for the next iterate, k plus 1. Well, how do you get it? You take the input brightness at that pixel, and then a sum of the neighbor brightness values, and you divide by some constant. So it's just a weighted summation of the neighbor values and the input brightness at every iteration. So I do and of course, you know, as a recipe, you could have suggested that in the first place for denoising images, but then no one would have understood what is this actually aiming at, this recipe. Here, the good thing is that your pixel update recipe falls out naturally from an optimization criterion. And this is where we differ drastically from the more classical image processing techniques, which would have suggested this or similar update schemes without any sort of understanding what this is aiming for. Often in the historic papers, the author knew what he was aiming for, but when he gave you the recipe, he didn't tell you. Or maybe he didn't even know what he was aiming for. And here we know what we're aiming for, and we know that if we keep iterating this, it will converge. Something that in a more classical processing approach you never know. You know, if someone defines an iterate, how do you know this is going to converge? Here we know. Why? Because the energy is convex, and because the Jacobi method provably converges. I said this is easily parallelized. Basically, you do this update for all pixels I at the same time, or you know, if you have a GPU, as many pixels as you can process in parallel, you do them in parallel. There are other algorithms that are slightly faster. So if you look at what we do here is we first compute the value u at pixel I at iteration k plus 1, and then k plus 2, k plus 3 for all pixels. And we always take the old pixel values. But if we have a CPU implementation of this algorithm, then we actually update each pixel one by one. And one thing we can do, and this is what the Gauss-Seidel method does in contrast to Jacobi, it does almost the same, except at every update, it uses all the new information it has. And so if you update the pixels one after the other, by the time you get to this pixel, you already have new values for these neighbors. And you have no new values for the one above and to the right. But depending on how you sweep, at least some pixels already have a new value. And it's kind of stupid if I know that by iteration it converges to the correct solution. Why, if I already have the value at pixel j for k plus 1, why should I not use it, right? Since the iterations get to a better and better solution, I should, in each update, use all the knowledge I have. And so this is the Gauss-Seidel method. This is the same update rule, except I split into the old pixels and the new pixels. So the pixels that were already updated, the ones, say, if I have an order of pixel, let's say in increasing order, so J means I've already J smaller one, I means I've already updated this, and J larger I means these are pixels. So this is the pixels J larger I up here and to the right, and this is J smaller I are the ones I already did. And so for the pixels I already did, I used the new update, the new value, sorry, at k plus 1. And for those that I didn't update yet in sweep k plus 1, I used the old values. I don't have any new values, right? And so this is an update scheme, is a slight variation of this Jacobi solver, and it's called the Gauss-Seidel method. It's a different way to iteratively solve equation systems that is slightly different from the Jacobi solver, in that you always use the most recent information for every pixel. Of course, depending on how you sweep the pixels, you will get slightly different solutions. I mean, it converges to the optimum, of course, but in each iteration you will get a different solution. So if I sweep them from below like this, I get a slightly different result for iteration k than if I sweep from above. But it doesn't really matter, you know, upon convergence it all converges to the right solution. The next problem is that this update, since I separate the old and the new ones, is no longer parallelizable. At least not directly. There are variants of the Gauss-Seidel method that can actually be parallelized. There is one variant, it's called red-black. I think it's called red-black Gauss-Seidel. It basically means that I split the grid into like in a checkerboard, and I update the black pixels in one sweep and the white pixels in another. And that I can do in parallel. So I can update all the black pixels at the same time. They only use the neighbor information from the white pixels. So I can use the latest, and this is called the Gauss-Seidel method. And it's parallelizable, because you can run all the white pixels and all the, it's called red-black. I don't know why, you know, the checkerboards I know are white-black, but doesn't matter. There is another variant I wanted to mention of this Gauss-Seidel method, which is very clever, a very simple trick that actually accelerates the process. The idea, and this is called the successive over-relaxation, the idea behind the over-relaxation is that in my space of functions U, let's call this the U space, these are my functions where I've solved the problem, I have an iteration. So here is U at time 0, here is U at time 1, here is U at time 2. And the idea is that in the process of iteration, it converges to the optimum, U optimum somewhere here. And now the intuition behind the SOR method is that somehow all these iterates go more or less in the same direction. And so one of the things you can do if you're saying, well, this process is heading in some direction in my space U, I can in each iteration extrapolate a little bit, go a little further than what the Gauss-Seidel would tell me. So very simple strategy. If this is the update of the Gauss-Seidel, here I call the Gauss-Seidel updates U bar, so this is U bar. Then I say, well, the algorithm told me from the last solution to the next one I should go here. Why don't I go a little bit further and take that as U1? And then Gauss-Seidel tells me U2 is here. U2 bar is the update by Gauss-Seidel. And again, I go a little bit further. And so in each iteration, I just do a little more than what the algorithm told me. And mathematically, you can write it in this way. It looks a little bit unintuitive at the first glance, but it basically means if I take UIK as the old update, then I take, you can rewrite that, and then you have UIK. Oh, sorry. plus omega times ui bar k plus 1 minus ui k. Right? So basically you take the value, the old value, this is uik, and then you take the update, this is the difference vector from the old value to the one that Gauss-Seidel told me, and then I take omega times that value. And if you take omega equals 1, you do exactly the Gauss-Seidel update, and if you take omega larger than 1, you extrapolate. Theoretically, you could also take omega smaller than 1, of course, but typically that will not accelerate it, but make it slower. This, I should say, is a pure heuristic. There is some studies and work on understanding successive over-relaxation. It turns out it's very hard to actually prove that this strategy is provably better. But in practice, it is better. In many applications, to the extent that there is even a prominent factor, I believe it's omega is about 1.67 or so, that seems to work magically for a lot of these algorithms. It's often very easy to check what's good omegas. You just run the algorithm upon convergence for some image, and then you try the same algorithm with different omegas and see how fast does it get to the solution. And if you do that for many examples, you will find 1.67 is magically the best value for omega in that range. Of course, in practice it's going to vary, but it's actually, to my knowledge, there's no proof that this is a good value or that this provably accelerates it. Yes?
So omega kind of have to relate to the epsilon, so we don't always go too far.
The termination criterion epsilon, maybe yes. I don't actually think it's much related. In practice, you would implement this with 1.6 or 1.67, and that, like for example, for what we do is for these kinds of problems and more general problems, we take the Gauss-Seidel method because it's faster than the Jacobi method. We take the SOR variant of it, because it accelerates it even further. But then we use a red-black version so that we can run it on the GPU. And so in the end we have SOR with typically 1.67 running on the GPU in this red-black fashion, where you update all the black pixels and then the white pixels of a checkerboard. But these are often experimental findings. So at least for the SOR, I believe there is very little theory behind it. It's just an experimental finding that it tends to make it faster. And so with that, you can easily solve these problems for even larger images in real time, and you can do image denoising basically on the fly. A little bit more, maybe just so that you've heard some terminology, will not go into details. There is other algorithms. There is a so-called preconditioned conjugate gradient method, which modifies the standard gradient descent. We'll talk about that a little later, in a way that you go into orthogonal directions, and for some methods this terminates exactly, and you have then a finite number of steps. There are multigrid methods for certain denoising problems. It turns out multigrid is useful. The idea is that you don't solve the original denoising problem on a very fine pixel grid, but you solve the same problem on a coarse grid, and then use the coarse solution as initialization for your finer solution. Here we initialized with the input image. But of course, if you have a somewhat denoised image, that's a better initialization. It saves you some iterations in your Gauss-Seidel method. And so if by denoising a coarse version of the image, you get an initial guess of what the smoothed version should be, you can use that on a finer grid as an initialization, and then you have like a coarse to fine hierarchical processing. And so the ultimate speed up might be that you take the SOR with an extrapolation factor with this red-black version on the GPU, and then you run it on a coarse-to-fine scale. So you see it adds a little bit in terms of programming that you have to do, but it may make things faster. And which strategy in the end for which problem is really the fastest is often a matter of trying and of experience. And I should say I'm not really an expert on numerics. There are people who spend all day doing numerics for various problems. We have experts here in the building as well who work on numerical optimization and who have a lot of expertise of knowing when is which solver the best choice. In the end, as you can see, I mean, all of these iterations converge to the optimum. So it doesn't, you know, if all you are interested in is finding the optimum and you don't care exactly how fast it runs, but you maybe care more about how much time you spend programming, then you might revert to some simpler solution that is maybe slower, but, you know, it can be implemented in half an hour. So there's many choices and trade-offs that you have to make as a programmer depending on what are the requirements. And so I said here, which combination of these techniques actually leads to the fastest solution. It depends on what is the optimization problem, what class of cost functions are we looking at, and it depends on what hardware do you have. If you have a GPU, then parallelism is important. If you don't, then it doesn't matter. So for example, Gauss-Seidel and SOR tend to be faster than Jacobi, but at least the naive Gauss-Seidel is not parallelizable. The red-black version is indeed parallelizable. So now we get to the same denoising, but in a spatially continuous setting. So space is a continuum. We don't have pixels anymore, but we have functions defined on a subset of R2, brightness values in the real numbers, and we want to do the exact same thing. And this is why I started with the discrete formulation first, to give you an intuition of what's behind it. This is the continuous version. You see it's the same, essentially same thing. We have a data term, the first one here, and a smoothness term, and you recognize the lambda is the weight of the smoothness term. The data term, we said before, for every pixel u and f should be the same or similar. So, and we penalized it in a least squares fashion. Here, same thing. For every pixel x, u and f should be similar in this least squares sense. And then, rather than summing over pixels in a continuous setting, we get integrals. But by now, integrals should not frighten you. It just means you're summing. And so, whereas before we summed over the pixels, now we integrate over the pixels. The smoothness, we said before, the brightness should be similar to the four neighbors in a regular grid. Here we say the gradient should be small. And if you recall, how do we discretize the gradient? If we do symmetric differences, well, we take the difference between the neighbors. Or if we do the forward difference, for example, we take the pixel and its right neighbor to the right. So this is a spatially continuous analog of this quadratic cost function we had in the discrete setting before. What is different now is that now we have a cost associated not with a vector u containing brightness values, but with a function u. And that does play an important role. And this mapping that assigns to each function u a value is called a functional. So I wanted to mention this term, functional, and so there is actually a lot of mathematics that was developed for this setting. Functional analysis, for example, is a class that you could take. The question that we will look at, we will not go into all the aspects of functional analysis in our class, but one of the aspects we want to look at is how do we minimize functionals? So how do we do the minimization if our space is infinite dimensional? So if our optimization space here, the functions u are not just numbers, not just vectors, but really functions. And this will occupy us for this class and the next class. And so to recap, I wrote it here, a functional is a mapping E which assigns to each element of a vector space, so the functions form a vector space, an element from the underlying field. And of course we had vectors before. In a discrete setting, the vector of brightness values is also a vector, so a vector space. Here the aspect is that that vector space is infinite dimensional. Let's consider a particular class of functionals, and these we will call the canonical class of functionals. It's functionals of this type that aggregate some information over the image grid. A summation or integral over all the pixels, and at each pixel I basically take this Lagrangian, it's called L. In our setting, to relate that to the previous slide, this L is just the data and the fidelity term evaluated for each pixel. So u of x minus f of x squared plus lambda times u prime I call the gradient. If we go to one dimension, I'll work for now in one dimension. Again, just like in the discrete setting, u prime is just the derivative, is du by dx. So u prime is nothing but du by dx. So the denoising problem is of this form. But you can imagine, and this is why we want to treat this class of cost functions, because the theory we will develop should be independent of what exact cost function we use. Whether we use a square here or no square shouldn't matter. Whether we use a square there or no square doesn't matter. What exact cost function we have should not be important. It's of this class. Some quantity evaluated for each pixel and then aggregated over all pixels. And this quantity in this example will depend on u at the location x and the derivative at the location x. But in general, of course, and the theory can be generalized to problems where I also have the second derivative of u in here. So u double prime, u triple prime, etc. You can do that, of course. But for now, let's consider this problem. U and the derivative of u. Now we saw earlier that if we have this extremality principle, dE by du equals 0, in a vector space it actually implies that the derivative should be 0 in each direction. dE by du1, by du2, etc. should all be 0. The question is, what happens to this concept if we get into infinite dimensions? Do we have infinitely many equations? Essentially we do, but the question is, how can we formalize that? And so this is the challenge in functional optimization, is how do you actually define that derivative? How do you define dE by du if u is a function? So this is the question that we want to address. And one should say there are many ways to define this derivative. The definition that I decided to present for this class is a definition that, at least to me, has always been very intuitive. It's a definition that was promoted or introduced by a French mathematician, Gateau. And interestingly, as you can see here, it was published, he died in the Second World War, 1914, and when they found these papers after his death and decided to publish them under his name. So this was published, as you can see, in 1919. And there is a short introduction by several very famous mathematicians of the time, Hadamard and others. So I put the link here. It's actually a historically interesting document to look into. And in this document, it's a very lengthy document, I should say, but one of the aspects that Gateau introduces is the notion of a functional derivative in a direction h, let's call it. Why is that useful? Well, we have infinitely many dimensions, infinitely many directions, so we want to say that the derivative at the extremum, the derivative must be 0 in each direction. And this is now requires a certain degree of abstraction to understand what this derivative means. You probably recall the definition of derivative. Typically in high school you would say df by dx. If f is a function of a scalar value x, you define it as limit epsilon going to 0, f of x plus epsilon minus f of x divided by the step size epsilon. And we can do the same here. So we go u plus epsilon minus u divided by epsilon, but what you see is we take epsilon in the direction h. What does that mean? What it means is, or one way to intuitively understand it, if this is your function u of x, so here we have x, here is u of x, then what we do is we perturb that function infinitesimally by an amount epsilon in some direction. And direction in the space of functions means that you add, for example, a function h that perturbs the initial configuration u in just one location maybe, or in a certain neighborhood only. And that size will be epsilon. And we can perturb it in many different ways, many different functions h that we could potentially add, scaled by epsilon. And then, because otherwise it doesn't make sense, right? You cannot take a function and add a constant value that in some sense that there are infinitely many directions, and so you have to specify the direction. Or if you have a vector u, adding a vector and a scalar doesn't make sense. So this is called the directional derivative. So it's the derivative of E with respect to U in direction H. And so the key idea of this Gateau derivative is to basically boil down the functional derivative to something we are familiar with. To just a standard derivative. In one dimension we know how to do derivatives. This is the definition, and so we select one random direction h, and then we compute the derivative in that direction. But what we should keep in mind is that there are infinitely many directions and dimensions to the problem. Just like in vector valued analysis, this directional derivative can be interpreted as the projection of the functional gradient on the respective direction. And in some sense, what Gateau does here is he implicitly defines the functional gradient by saying, take this expression for the directional derivative in h, and that should be the same as the projection of the functional gradient onto h, onto the direction h. And projection in a vector space, in that function space, is nothing but the scalar product. It's this function dE by du times the function h, and then integrated over x. And what we will do in the following, I think I will do that today, is we will use that definition to extract an expression for dE by du. Looks a little bit lengthy, but what we do is as follows. We use that definition. Here I put it again, dE by du in direction h. Here it is. And then we plug in here the functional that we assume of this canonical form, integral L dx. So E of u plus epsilon h will be integral L of u plus epsilon h and u prime plus epsilon h prime. minus integral L of u, so that would be this E of u here. Right, so all we do is for these two energies we plug in this expression, and we keep in mind if we perturb u by epsilon h, then similarly the derivative is perturbed by epsilon h prime. And then what we do is we assume epsilon goes to 0, so these perturbations here all go to 0, so we do a Taylor expansion, a linearization in epsilon h, and if you do that in the first term, then you get L of u and u prime, so the original location where we do the expansion at, and then plus the change epsilon h times the derivative with respect to u, plus the change epsilon h prime times the derivative in the second argument. You may be familiar with Taylor expansion. The standard Taylor expansion basically says that if I have a function e of u, or let's call it f of x plus epsilon, then this is approximately f of x plus epsilon times f prime of x plus terms of order epsilon squared. And here we do the same, except that our L has two components, right? U and U prime, and so we have a Taylor linearization in both of these components. And then we have terms of order epsilon squared here, and then minus L of U. And then as you see, the L cancels out, right? And then if we divide by epsilon, the epsilon here disappears, and here we get a term of order epsilon which goes to 0 in the limit. And so all that remains is the L by du times h plus the L by du prime times h prime. And now what do we want? Let's go back one slide. We want to express that whole directional derivative as a projection onto h, so as something multiplied by h times dx. If we go here, we have that already. We have some expression multiplied by h. Here, however, we have h prime, but what can we do? We can do integration by parts. H prime is dh by dx, so we can carry the derivative over to the first term, ddx of dl by du prime, and then we just have h here. So this should be read as the derivative being applied to just dl by du prime. Of course, we assume for this to work, as you know, integration by parts means the sign changes, and then as you may remember from high school or wherever you had integration by parts, there is boundary terms. But we'll assume for now that h is 0 on the boundary, so there are no boundary terms, which means in practice we consider perturbations in our domain omega which are such that u is fixed at these boundary values, so h is only non-zero inside. We'll come back to the question of boundary conditions later, but for now we assume h is 0, so then this converts to that, and now we can extract h, right? We can pull it out, and what we end up with is h times this thing in the brackets. And now in the previous slide I argued the directional derivative is the functional gradient projected onto h. And so this whole derivation tells us that for this class of energies, this is the functional gradient. It's dl by du minus ddx dl by du prime. And now we said the directional derivative must be 0 at the minimizer, and it must be 0 for any direction. This is important. Optimality in multiple dimensions, you need the derivatives must be 0 in all directions. For example, if you're on a hill, let's say you have 2 degrees of freedom in your optimization problem, then of course in direction of the level lines the derivative is 0. It doesn't change, but that doesn't mean you're at a minimum. You're at a minimum or a maximum only if the derivative in both in any direction doesn't have an effect, doesn't change. So the energy doesn't change in any direction. And so in other words, for this to be an extremum principle, we now want this derivative to be 0 for any choice of function h. And now the idea is this expression is 0 for any h if and only if the term in the brackets is 0. Otherwise, if this term is not exactly 0, then I can always find some h such that this is non-zero. If this has a value epsilon at some location x, then I just take a delta function that is located at that point, and it will give me the epsilon. So then it's not going to be 0. So you can clearly see if you take just delta functions for h located in different places, you see this term must be 0, otherwise you don't get 0. And so we can read out the extremality principle for functionals is dE by du equals 0, and it basically means that term in the brackets here must be 0. This term here must be 0, and so this, what I put in a box here, is called the Euler-Lagrange equation. And so the Euler-Lagrange equation that you see here, that is the extremality principle for functionals, and we just derived this in this Gateau calculus. And this is where we'll stop and continue next time. Thank you.